Hey, welcome back to your favorite pre-calculus class. We're going to talk about the real zeros of polynomial function today. We're going to start out with the division algorithm for polynomials. You're probably more familiar with this with the division algorithm when you're just working with real numbers. So like if you go 13 divided by 4 and you do that with long division, 13 divided by 4, we know 4 goes to 13 3 times 4, 12. Make sure that we subtracted that. 13 minus 12 is 1. There's our remainder. So 13 divided by 4 is 3 plus remainder over divisor, but we just wrote that as a mixed number, 3 and 1/4. I'm just trying to show you the division algorithm for polynomials is similar. If you take a polynomial f of x, you divide it by g of x, you get q of x, the quotient. So this is your dividend. This right here is your divisor. Here's your quotient. And then you do all the work and you get the remainder right here. All right, here's your remainder. Whoops. Okay. So you can write that. F of x divided by g of x is q of x, the quotient over here, plus remainder over our original divisor right there, q of x, right? Another way to write that is in the alternative form. If you multiply both sides by g of x, this by g of x, this by g of x, this by g of x right here, then the dividend equals the quotient times the divisor plus the remainder. In other words, 13 equals the quotient 3 times the original divisor 4 plus the remainder 1. That's right, if you're doing that with the real numbers. So let's see how that works with some, this plays into your remainder theorem, okay? So if you take f of x, you divide it by x minus c, then the remainder is f of c. So according to the division algorithm, if you take f of x, you divide it by g of x, you get q of x, the quotient, plus the remainder over the original divisor g of x. So if we divide by, we're dividing by x minus c, so that's our g of x. I take f of x, I divide it by x minus c. I get my quotient plus my remainder over g of x, my divisor, which is the x minus c. Now let's put this in the alternative form of the division algorithm. So let's multiply everything by x minus c. This by x minus c right here. This by x minus c, both sides by x minus c. So we got f of x equals x minus c times q of x, quotient, plus our r of x, remainder. Let me take that up here. Now, if I divide by x minus c, this says, then the remainder is f of c. So let's plug in f of c then. Let's put c in for x. So c goes in for x. So right here I got a c now. I got c minus c times q of x here plus r of x. I'm going to call this r of x just my remainder, capital R. So f of c equals, notice c minus c is 0, 0 times q of x, that's gone. So f of c is our remainder. So anytime you divide by x minus c, your remainder is actually f of c. Okay. So that brings us to the factor theorem. So if x minus c is a factor, if and only if f of c is 0. So that's two separate statements. So if the remainder is 0, then x minus c is a factor. Okay, let me give you an example. So let's take, I don't know, let's take 20. All right, if I take 20 and I divide it by 4, right, I know my remainder is 0. So if I take 20 and divide by 4, that's my factor, 4 is my factor. Then if the remainder is 0, okay, then 5 is also a factor. Now, I got to do this, though, with polynomials because I'm dividing by something of the form, a linear polynomial here. So let me give you a different one with polynomials. So if I take x squared plus x minus 2, for instance, and let's say I divide that thing by x minus 1. Okay, and I do the long division. So I'm matching the x squared. So x times x squared, x times -1, negative x. Don't forget to change your signs here if you remember your long division. Bring down that minus 2. Now what times x gives you 2x? Positive 2 does. 2 times x, 2x. 2 times -1, negative 2. Don't forget, change your signs. Hey, there's our remainder. 0. So, since I took there's my function. I divided by something of the form x minus c, so my c here is 1, and I get a remainder of 0. That means x minus 1 is a factor of this thing, right? And you know that because since it's a quadratic, we really could have just factored this. Right? If we were to factor this thing, we're like, okay, x and x, factor at minus 1 plus 2. Oh, look at that. X minus 1 is truly a factor. And why is it a factor? Well, my remainder is 0. So if f of c is 0, x minus c is a factor. So the remainder's got to be 0 for it to be a factor. And you can plug in that c. So since f of x is x squared plus x minus 2, we're dividing by something of the form x minus c, in this case x minus 1. So our c is 1. If I plug 1 in, it'll tell me, it's a 1, my remainder. So 1 squared plus 1 is 2, 2 minus 2 is 0. It tells me my remainder right there when I plug that c value in. So let's do these ones right here. Let's use the factor theorem to determine whether the function has a factor. If x minus 1 is a factor, then when I do the division, 2x cubed minus x squared plus 2x minus 3, when I do this division, I got to get a remainder of 0. If I get a remainder of 0, x minus 1 is a factor. So I say, what times x gives me 2x cubed? I say 2x squared does, and I multiply it through. 2x squared times x, 2x cubed. 2x squared times negative 1, negative 2x squared. Don't forget to change those signs. Bring down that 2x. Now I'm matching the x squared. What times x gives me x squared? Positive x does. X times x squared. X times negative 1, negative x. Don't forget to change those signs. Bring down that minus 3. What times x gives me 3x? 3 does. So 3 times x, 3x. 3 times that, negative 1, negative 3. Don't forget to change your signs. Hey, look at that. Remainder 0. So, x minus 1 must be a factor. X minus 1 must be a factor. And if you wanted to, you could have also, and I went through this long division for a reason you'll see later, you could have, since you're dividing by something of the form x minus c, again the c must be 1, you could have plugged 1 in to this, and you would have got a remainder of 0. It would have shown you that remainder right there. Okay. In this case, when you're checking is x minus x plus 2 a factor, what is your c here for this one? Well, think about x plus 2 as x minus negative 2. So the c is negative 2. So you could plug in negative 2 on this one. But what I'm going to do here is I'm going to erase this. And we're going to do this one with synthetic division so we can shorten our division process and remind you about that one. Okay. So now we're going to go 2x cubed minus x squared plus 2x minus 3. We're going to divide it by x plus 2. Sorry about that. I can't answer that right now. So we're going to divide by x plus 2. So what's our, when we did synthetic division in the box, we would put our k. We called it our k, or you can call it your c, whatever you want. It's got to be of the form x minus k to do synthetic division. So our k here is negative 2 in this case. And then what we did is we took all our coefficients and we put them on the top here. 2, negative 1, 2, negative 3. And it's got to go down in descending order perfectly. 3rd degree, 2nd degree, 1st degree, 0th degree at the end. That's a 1st degree right there and 0th degree at the end. If you don't have a degree, you got to put in 0 up there. And then we're looking right here. We're looking for our remainder. What's our remainder? Right there at the end. If it's 0, x plus 2 is a factor. If it's not 0, then it is not a factor. We drop our 2 straight down. We take that 2 and we multiply it by the negative 2 in the box. 2 times negative 2, negative 4. And then we take the negative 1, we subtract the 4, we get negative 5. Negative 5 times negative 2 is 10. 2 plus 10, 12. 12 times negative 2, negative 24. Negative 3 minus 24, negative 27. That's our remainder. Is the remainder 0? No. If the remainder is not 0, x plus 2 is not a factor, right? Got to have a remainder that is 0 on this. Alright, so rational zeros theorem just says we can list all the possible rational zeros by taking all the factors of our a subscript 0, our constant on the end, over our factors of the leading coefficient. And once and that's how we can list them all. So for example, f of x equals 2x squared cubed plus 11x squared minus 7x minus 6, all our possible rational zeros will be factors of 6 over factors of the 2 right there. Or factors of 6, factors of negative 6, they're the same because, for instance, 1 times 6, 1 times negative 6, so 1 and negative 6 are factors, 1 times negative 6, negative 6. So is negative 1 and positive 6. Right, so you got to have the plus minus on both of those. So factors of 6 will be 1 and 6, 2 and 3. Let me list those in order here. We'll go 1, 2, 3, and 6. Factors of 2 are course of 1 and 2, both positive 1 times positive 2, negative 1 times negative 2. So we're going to have plus minuses on all these. So we're going to take factors of 6 over the factors of 2 each time. So for instance, plus minus, I got the 1 over the 1, plus minus the 2 over the 1, plus minus 3 over 1. These are all possible zeros. Plus minus 6 over 1. And then I do it all over 2 this time. So plus minus the 1 on the top over the 2, plus minus the 2 on the top over the 2, plus minus the 3 on the top over the 2, plus minus the 6 over 2. I look and see if I have any repeating. Did I list any twice? And I say, well, 6 over 2 is 3, and I've already listed 3 up here. 2 over 2 I've already listed right there is the 1. Right? So it looks like I have 1, negative 1, 2, negative 2, 3, negative 3, 6, negative 6, half, negative half, and 3 halves, negative 3 halves. These are all possible zeros. And we're going to use those possible zeros so that we can factor this thing using our division algorithm and the factor theorem. So let me erase a little bit of this here so I have a little bit of room. So if you keep in mind your possible zeros there. Okay, we're going to try those one at a time here. Okay, so I'm looking at the 1 and the negative 1. I say, well, let's start with, we're trying to factor this 2x cubed. You can't see that very well. That is a positive 2x cubed. 11x squared minus 7x minus 6. We're trying to figure out what our factors are. All right, so it's kind of like if I had 12 is 3 a factor, right? And I say, well, 12 divided by 3 gives me 4 with no remainder. In other words, 3 times 4 is 12, right? So what we're going to do is we're going to see if, let's try negative 1 first. Is negative 1 a factor? Well, if negative 1 is a factor, then x minus negative 1, I'm sorry, if negative 1 is a 0, then x minus negative 1 is a factor. In other words, x plus 1 is a factor, and it'll have no remainder. So I got to do the division on that. So I'm going to try negative 1 in the box. I'm going to do this division. So I'm going to take 2x cubed plus 11x squared minus 7x, 2x squared, 2x cubed, I'm sorry, plus 11x squared minus 7x minus 6. And I'm trying to see, is my remainder 0 right here at the end? If it is, x minus negative 1, in other words, x plus 1 is a factor. If the remainder is not, I got to move on to the next 0. Drop the 2 down. 2 times negative 1, negative 2. 11 minus 2, 9. 9 times negative 1, negative 9. Negative 16, 16, 10. Uh-oh, that's not 0. So I throw out x minus negative 1. So negative 1 is not a 0. Okay, so that's not a 0. and I move to the next one. Well, -1 didn't work. It was a possible rational zero from my initial possible rational zero list. Let's try +1. I tried -1, it doesn't work. +1. Well, if 1 is a 0, then x minus that 1 must be a factor. And now I put the 1 in the box, x minus c, 1 is my c, and I do the division again, 2x cubed plus 11x squared minus 7x minus 6. I'm dividing it by x minus 1, but I'm using my synthetic division. Drop the 2 down, 2 times 1, 2. 11 plus 2, 13. 13 times 1, 13. -7 plus 13, 6. 6 times 1, 6. -6 plus 6, 0. Hey, there we go. It worked. There's no remainder. This is my quotient. It's 1 degree less than the original function, so 2x squared plus 13x plus 6. That's going to go right here. 2x squared plus 13x plus 6. So there's our quotient, okay? And now we're trying to write this thing in completely factored form. So if you forget about this for a minute, so we have x minus 1. And since I have a quadratic, what I'm going to do is I'm just going to factor this 2x squared piece. So I know it's 2x and x. And then I'm looking at that, and I'm like, well, let's see, factors of 1. Let's try 1 and 6. It's got to be either plus plus or minus minus. Looks like it's a plus plus. So there's our, this is in completely factored form right there. X minus 1, 2x plus 1, x plus 6. Just wrote it in factored form. I should have blown that up. Forgot I could do that. So can we find the real zeros for this one now? Okay, so this is our approach, because when you've got these larger polynomials, larger degree polynomials, that's just how you want to approach these. You want to list your possible zeros. So all the factors are 36 over factors of 1, right? So you got your 36 is a factor, or 1 and 36 are factors. 1, 36, you got 2 and 18, you got 3 and 12, you got 4 and 9, you got 6 and 6, right? You got factors of 1 here, just 1 and 1. And now we're working this thing, and so we're going to try, let's go 1 over 1, positive 1 over positive 1. Then we'll try -1 over -1 after that. So let's try 1. If 1 works, okay, if 1 works, so here's our x to the 5th minus 7x to the 4th plus 19x to the 3rd minus 37x squared plus 60x minus 36. If 1 works, then x minus that 1 is a factor. Okay, so we're going to go to the side, we're going to try it 1. We got 1, -7, 19, -37, 60, -36. And let's see what our remainder is. Drop the 1 down. 1, -6, -6. We got 13, 13. What's that? -24, -24. That's got to be 36. 36. Hey, what do you know? 36. There we go. Remainder 0. The remainder is 0. So x minus that 1 right there is a factor. Let's write the answer. So 1 x to the 1 degree less, 4th, minus the 6 x to the 3rd, plus 13x squared, minus 24x, plus 36. Okay. Now from there, we can check 1 as well. Sometimes you'll have a repeated 0, or you can move on to -1. Well, let's just try the 1 as well. Well, if 1 works, we already have x minus 1 as a factor. If 1 works, then x minus the 1 will be a factor. So what we're doing now is we're taking this x to the 4th, we're dividing it by x minus 1. And we're going to see if that remainder is 0. So 1, -6, 13, it's a 13. -24, 36. If this doesn't work, we know it's not a repeated 0, and we move on to -1. So 1 comes down, 1 times 1, 1, -5, -5. Oh, what was that? 8, 8, negative 16, negative 16. So looks like it is not a repeated 0. So that's out. So I would erase, I get 20. So this is out. And now I'm going to move on to 2. So now I would try 2, and I run through this process. And it doesn't work. And I'm going to cheat here and look, I try negative 2, right? Because now I'm trying the 2 over the 1. It didn't work. I tried the negative 2 over the 1. Tried the negative 2. Didn't work again. And so I keep trying this. I move into my 3. Erase some of this here. I wish I had more room on this. I try 3 now. So if 3 works, then x minus 3 is the factor. So 1, negative 6, 13, negative 24, 36. 1, 3, negative 9, 4, 12, negative 12, negative 36. Hey, what do you know? Remainder 0. How about that? How did he know that? Crazy. So we've got the 1x to the 1 degree less than the 4th right here. So 1x to the 3rd minus 3x squared plus 4x minus 12. Now we're to a 3rd degree. So again, you can try the 3 again, or you can move on to the negative 3 if the 3 doesn't work, and so on. But I'm noticing I've got 4 factors here. 4 terms, I'm sorry. So I'm going to go back to my factoring approaches, and I got to think to myself, oh, I wonder if factor by grouping would work. Sometimes if you got 4 terms, factor by grouping would work for you. So you got this x minus 1, you got this x minus 3. Let's take a look at these two. What could I take out of those two? Both of them have an x squared, and I'd leave you with x minus 3. And then both of these two have a 4, leave you with x minus 3. So you've both of these terms, that term and that term, have an x minus 3. So an x minus 3 comes out, and you're left with the x squared plus 4. X squared plus 4 right there. You still got this x minus 1, you still get this x minus 3. And then you look at that x squared plus 4, which does not factor itself. So this thing right now is in completely factored form because the x squared plus 4 does not factor. Boom, right there. Completely factored form. So if you're finding the real solutions of the equation when you set that thing equal to 0, and we just did this exact same one, so we have this factored form. What was that? X minus 1. We had x minus 3 and another x minus 3. So there was 2 of those x minus 3s. And then we have x squared plus 4. This is equal to 0. So you just take each one of those, set equals 0. X minus 1 equals 0. That means x equals 1. You got 2 of these x minus 3s. So x minus 3 equals 0. X equals 3. And again, there was 2 of those. And so what you say is x equals 3 with multiplicity of 2. We'll kind of get into that later, what that means. That just means you have 2 of those, an even amount. And then x squared plus 4 equals 0. Again, this one did not factor. So if you were to solve this, you've got, look at that, you've got a plus minus. This is your 2i, your imaginaries. We're not working in the imaginaries right now. We're just looking for the real solutions, so we can't write that one in yet in this section. If you hold on a little bit, we'll work with some imaginaries later on in the course, okay? So every polynomial can be uniquely factored into a product of linear factors and or irreducible quadratics. Just like in that last one, this was an irreducible quadratic. The other ones were linear factors, right? X to the 1 power minus 1, x to the 1 power minus 3, and so on. All right, that brings us to the intermediate value theorem. So this intermediate value theorem says if you've got f, a continuous function, on a closed interval from a, I'm going to write on this, up to b, okay? And if you pick some k that's in between, let me label my f of a. Here's my corresponding y value for a. Here's my corresponding y value for the b, my f of b, right there. if I pick a k in between those, so k is less than or equal to f of b, greater than or equal to f of a. So if I pick, let's say my k is right here, and this thing's continuous, right? So this thing is continuous. I never lift my pencil when I draw that thing. Then, so this is your then, there exists, that means there exists a c value in between, so this is element of, that's an element of, in there, in this interval a to b, such that f of c equals k. So let's revisit that again. I'm picking a k that's between f of a and f of b. Then, if this thing is truly continuous, I'm going to take on all these y values in between f of a and f of b, including the k. So there's got to be a corresponding, there's got to be a c in here, such that, because this is c comma f of c, that's that point, such that this f of c right here is that k value, such that f of c equals k. So that's all it is saying. If I pick a k in between those y values, there's some c over here such that its corresponding y value is hitting that k. Okay. So another way of stating it, or a use of this intermediate value theorem is saying, well, if I'm going from a negative to a positive, it's got to hit and have a 0 right there. Right, my c value is going to hit 0. I'm going to have an x-intercept right there. So you can use that to show or to prove that you have a 0, in this case, between 1 and 2. Okay, so for instance, the intermediate value theorem, if you recall, says, and we're going to use this, it said, so we're going to prove it. We'll be a little bit more formal than your textbook is. Since f, since that's a really bad sense, is continuous, because it's a polynomial, on this interval from 1 to 2. And we're trying to show that we have a 0, right? I don't know what this thing exactly looks like, but we're going from, we're going to find out, whoops, from 1 to 2. We're trying to show that we're going to have a 0, somewhere between 1 and 2. Okay, so we're either going from negative to a positive, or maybe it's vice versa, from a positive down through a negative at 2. So we're going to restate this intermediate value theorem. Since we're continuous on this interval from 1 to 2, and f of 1 0 is less than or equal to f of 2 and greater than or equal to f of 1, i.e., in other words, f of 1, if I was to plug 1 in, I'd have f of 1 up here. If you think about that, 1 to the 5th minus 1 to the 3rd minus 1, you got 1 minus 1 minus 1 is negative 1. So it's going from negative 1. And then if I plug 2 in, 2 to the 5th minus 2 to the 3rd minus 1, let's see, what's that? 32 minus 8, 24 minus 1, 23. So in other words, you're going from 1, negative 1 right down here, 1, negative 1. You're going from negative value up to 2. And it looks like this spits out a 23. Right? So you're going from a negative to a positive. You've got to be crossing right there. Right? At some point, because this thing's continuous, it's got to cross through and have a 0. So we stated, again, that since f is continuous from 1 to 2, 0 is between f of 1 and f of 2, then there must exist a c in between that interval from an x value of 1 to an x value of 2, such that f of c is what? What are we trying to prove? Such that f of c is 0. We proved that there's a 0. C comma 0, right? There's some c in there between 1 and 2 such that it is 0. And that's all we're proving, the intermediate value theorem. All right, we'll see you guys in class.